So, welcome to the second lecture on advanced experimental designs. In the first lecture, we have discussed till this point, and I initiated this portion also, right? So, now here, what we have to derive is MSE, mean square error, is equal to SP, right? So, SP stands for pooled standard deviation, pooled standard deviation, or we can say combined standard deviation also, right? So now before I explain this one, so let me go back to the t-test we have studied in our previous semester. Now we may have two types of t-test. The first one is for one sample t-test, that is for a single sample, and we have studied t-test for two samples. But here we have taken a number of samples, right? So now here we have a number of samples, right? So we have a number of samples, but we have studied t-test only for these two samples, right? So t-test. Now I am going to extend our t-test concept to a number of groups or experiments or treatments, right? Okay, now first we have to understand what these one sample t-test for an individual group, right? So now you see here one sample t-test, this is the equation. Now we should know t calculated, and we have to get the critical value from the t table also, right? So now the t calculated can be computed using this formula, x minus mu divided by a square root of n, right? So this is t calculated. Now let's say we have one sample and the sample size is n, its standard deviation is s, and the x bar is this, right? And we have drawn this sample from a population. Now let's say the population standard deviation is mu, right? So under inferential statistics we have to find out what this mu is, right? So here if you know this mu, or if you have any assumptions or specified value, we have to plug this value here and we can compute x bar from the sample. This also can be calculated and this will be given, right? So now for this sample we can calculate our the t value, the calculated t value, and from that we have to compare the value with the critical value, right? So if t calculated is greater than t critical, usually what we do, we will reject h naught, right? So what are our h naught and alternative hypothesis? H naught, let's say h naught mu is equal to okay, otherwise we can say the sample standard deviation is equal to mu, right? So here we are just assuming mu is equal to x bar, and our alternative hypothesis will be mu is not equal to x bar. It may be either. So here in this scenario, this is a two-tailed test, right? So now what we have to do is, we know x bar, and if you know the mu, at 95 confidence level we can test if our hypothesis is true or not, or if our claim is true or not, right? So if I do a simple example, let's say my x bar, right? So this is x bar is calculated by adding all the data points in the sample and dividing by the number of sample or sample size. I'm sorry, no number of sample size, number of observations in that sample, right? So let's say our x bar is equal to 15. This is what we calculated, and let's say from any means we have already known that mu is equal to 16. It's okay. So mu is equal to 16. Otherwise, if I take the other way around, x bar is equal to 16 and mu is equal to 15. Let's say I know the standard deviation s of this sample is 1.5 and my sample size is 10, and I'm going to test whether my sample mean is equal to the population mean at 95 confidence level. So my alpha is equal to 0.05, right? So now t calculated will be equal to x bar minus mu divided by s square root of n. Now here 16 minus 15 divided by s 1.5 square root of 10. So this will give me, let me calculate, 1 divided by 1.5 divided by square root of 10 is equal to, it gives me 2.108, right? So 2.108. Now I have to calculate, I have calculated the t, this is, I'm sorry, this is t calculated, and from the table I have to find the critical value. So t critical value, right? Okay, so I have just inserted the t table here. You can see. Now if you want to find out the t critical value, you should know the degrees of freedom, right? So if you have n number of, right, so degrees of freedom is equal to n minus 1 number of independent observations that are free to vary, right? Okay, and here 10 minus 1 9, and our alpha value is 0.05. so now what I have to do is, now this is alpha value is 0.05 here, right? And our degrees of freedom 9. So the t table is equal to 2.2, where is that, 62, right? So now we can conclude that our t table is where is that? Okay, so t critical is equal to 2.262, right? So if you compare this value and this value is less than our table value, the right? So t calculated is less than t table. So we fail to reject H naught. We fail to reject H naught. So we can conclude that our, right, so if we fail to reject H naught, we have to accept that, right? So at 95% confidence level, mu is equal to x bar. This is how we have to calculate, conclude it. Now if I extend this for 2 samples, now what can I do? Right, so this is the summary of what we have studied for one sample t-test, right? So I just took a simple example also. Now we will extend this to 2 samples, right? So under 2 samples, so this is the summary, right? So if you look at this summary, first in order to decide whether to perform t-test or z-test, we have to, right? So here what we have to check is, if you know, right, so if you know the standard, population standard deviation, we will always go for the Z test, right? So irrespective of whether the sample size is small or large. But if sigma is unknown, right, so this is the summary. So let me write down the summary here. Okay, so popularly we have t-test and z-test. Now z-test is for all the samples including the small and large samples when sigma is known, right? When sigma is known. But t-test, right, so the t-test can be for 1 sample and 2 samples, right? So we are going to just look at the 2 sample case now. 2 sample, okay, so whatever. Now what we have to do, right, so now we are not going to go for the 2 sample or 1 sample. Now we will just decide whether to go for t-test or z-test, right? So here, if you know the standard deviation of the population, we will always go for z-test. Now if you want to go for t-test, right, so let's say the first question we have to ask is, if sigma is known or not, right? So this is the first question you have to ask, and if the answer is yes, then you will always go for z-test. And if it is no, right, so if the answer is no, now we have to consider the sample size. Now if you consider the sample size, so it may be small or it may be large. Typically we will take n is equal to 30 as the thumb of rule. So if n is equal to less than 30, we will consider it to be a small sample, and if it is greater than 30, we will consider it to be largest sample, right? Okay, now if the sample size is small and if we don't know the sigma value, we will go for t-test, and if our sample size is large, we will go for z-test, even though if you don't know the the sigma value. In that case, we will just simply substitute s instead of sigma in the equation for the test statistic, right? So if you don't know the sample, if you don't know the population standard deviation, and if the sample size is large, if you can perform z-test, in that scenario you have to consider sigma is equal to s. Okay, right. Now coming to the two sample t-test. Okay, so here you can see we will be having two samples, right? So let me explain this here. Right, so we have to study now two sample t-test, right? Okay, now let's say we have two samples. This is the first sample and this is our second sample, and the sample size is n1, this is n2, and let's say this is x1 bar and x2 bar. Okay, and here, okay, so the population mean for this one is, okay, so this should have been drawn from a population and this should have been drawn from another population, right? So now what we have to consider is, based on the sample mean, we have to test if these two sample if these two population means are equal or not. So our null hypothesis is mu1 is equal to mu2, which means we are just assuming, right? We are just assuming whether the mean of the first population will be equal to the mean of the second population, and HA will be mu1 is not equal to mu2. This is a two-tailed test again. Okay, right. Now there might be two scenarios, right? So now, okay, so you see here, this is S1 and this is S2, right? Okay, so now let's say this is again SP. Now this is the pooled standard deviation for a number of treatments, right? So pooled standard deviation of a number of treatments can be written as summation I is equal to 1 to a ni minus 1 si squared divided by summation ni minus 1, right? So I is equal to 1 to a. Now you can write this as I is equal to 1 to a ni minus 1 si squared. Now here ni, right? So if you add all these things, that will give you the n, right? So that is what we already discussed here. You can see, right? So here if you consider this, n is the total number of observation, right? So n is the total number of observation, all these observations, right? N. Right, so n again, okay, so it can be extended as summation I is equal to 1 to a ni, in simple ni, right? So simple ni minus summation I is equal to 1 to a 1, right? So n here, this is equal to capital N, and this is again equal to n minus a, right? Okay, now if you consider this one, Si squared can be again written as Si squared is nothing but the standard deviation of all the data points in one group, right? So now Si squared can be again written as, now considering the data points, let's say this is the ith group, right? So here we have n number of observations. Now I can write, so the standard deviation within the group, right? So within standard deviation, within group standard deviation is equal to, I can write this as summation I is equal to, no, here not I, right? So j, right? J is equal to 1 to n, right? So what I have to do is, here we have x1 x2 up to xn observation, no, wait, I'm sorry, right? So if I consider one sample, let me use a different color, right? So let's say this is the ith group, right? So we have yi1, yi2, yi3 and so on, right? So till yin, and it has a mean that can be written as yi dot bar, right? So this is the mean of this group. Now in order to find the standard deviation of this group, what I have to do, yij, right? So I means ith treatment, but j represents 1 to n, right? So yij. Now yij means j is equal to 1 to n. So here the changing variable is only j, right? So yij minus yi dot bar holding squared divided by n minus 1. Why n minus 1? So here there is no problem, but if we have different number of sample size, here we have n1, here n2, n3 and finally n I, right? So here we have to put ni, right? But here there is no worry, so we can simply write ni minus 1, right? So here divided by n minus 1, right? So because it should be divided by its degrees of freedom, right? So if we have if we have different sample, I can write ni minus 1. But here ni is equal to, ni is a constant, but if it is different, then we have to put this ni, right? Okay. Now after finding the standard deviation of one group, now we have to find out MSE, right? So MSE means we have to find out the error of all these groups, right? So now what I will do is, I will just simply multiply this here, otherwise no need, right? Now I will add all of them, right? Summation I is equal to 1 to a, I is equal to 1 to a Si squared, right? So this tells the standard deviation of one group, and this will tell the standard, right, let me write here, standard deviation of ith group, and this will give me the standard deviation of between groups also, which will be the MSE, right? Means I mean the total of standard deviation of all groups. I can write that way. This will be the total of all groups standard deviation, right? So okay, now this can be written as, now I have just taken summation like this. Again, summation I is equal to, okay, both side I am taking summation I is equal to 1 to a, I is equal to 1 to a, that's all, right? So I is equal to 1 to a, summation j is equal to 1 to n, yi minus yi dot bar square divided by this summation belongs to this n minus 1 also. So I am just writing summation I is equal to 1 to a ni minus 1, ni minus 1. Now this is equal to summation I is equal to 1 to a, summation j is equal to 1 to n, yij minus yi dot bar square divided by, this is again equal to n minus a. I already explained you how to do this, right? Okay, now this is nothing but this is the degrees of freedom of all the observations that we have collected from the population. Okay, and this is the standard error. This is the standard error. Now if you divide this expression, this is the, actually this is the total of the standard deviation of all groups, and if you divide by the degrees of freedom within the groups, it will give you MSE. So this is nothing but mean square error, right? So this is nothing but mean square error. So now if you go back to our lecture note, so you can understand that, okay, so this is what I have explained now, right? So I hope you have understood. So starting from here we have derived this till this point, right? Okay, so now SSE, right? So SSE divided by n minus e, sum of squared error is this one, right? So sum of squared error is this one, right? If you add all the standard deviation of all groups, it will give you literally the error sum of square, right? So SSE divided by this within group degrees of freedom, it will give you mean square error. So mean square error, so from this we can tell MSE is the sigma head square, right? Okay, now one more thing. So what is our estimated standard deviation? So this is standard deviation, but head means estimated, that is SP, right? So that's why I told you under t-test of a number of treatments, we can tell that SP is equal to MSE, right? So pool standard deviation. So SP is sigma head square, right? So SP is equal to mean square error. Now if you consider the variance of this yi dot bar, right? So that is the variance of the ith group mean, the variance of ith group mean. Now let me create some space here by erasing. Okay, so now if you consider variance of yi dot bar, right? So yi dot bar means, now if I pictorially represent this, how will I do it? Right, so now we have a number of treatments. Now this is y1 dot bar, and this is y2 dot bar, and this is y dot bar, and let's say the intermediate position yi dot bar. Okay, so the variance of this yi dot bar is variance of yi dot bar is nothing but the population standard deviation divided by sample size, right? So that is population standard deviation divided by sample size n, right? So here I can write this as sigma squared divided by n by definition, but for this case variance, estimated variance of yi dot bar is equal to, what I have to do, summation I is equal to 1 to a yi dot bar. Now the grand total is y double dot bar, right? So yi dot bar minus y double dot bar square divided by a minus 1. Why a minus 1? Here we have to put the degrees of freedom. Okay, so we have already studied that this is our MS treatment, and this is our sum of square treatment, this is our sum of square treatment, and this will be our a minus 1. So from this I can tell, oh I'm sorry, this is not MS treatment. Okay, I'm sorry. This is actually not sum of square treatment. Okay, right. So now you can see here this equation. This equation says MS treatment is nothing but the sum of square treatment divided by a minus 1, right? So this is equal to sum of square treatment. Now here if you consider this one, okay, right. So look at these two equations, right? So from this equation I can substitute sigma square divided by n instead of this, right? So sigma square divided by n is equal to summation I is equal to 1 to a yi dot bar minus y double dot bar holding square divided by a minus 1. So now we know that this is our variance of yi dot, right? So this is our variance of yi dot, no, I'm sorry. Right, okay, so if I rewrite this equation like this, sigma squared, now I am going to multiply this n before this summation expression. Sigma squared is equal to n into summation I is equal to 1 to a yi dot minus y double dot bar holding squared divided by a minus 1, right? So now you have to know that this is our population standard deviation, right? So this is our population standard deviation, right? So if you look at this one, carefully, now what does it say, tells? Now we have n number of n here, this is equal to sigma squared divided by n again, right? Okay, yeah, okay, now this is equal to variance of yi dot bar. This expression is equal to variance of yi dot bar, and we know that yi dot bar is variance of yi dot bar, that is directly equal to sigma squared divided by n, right? So now I can write sigma squared is equal to, now here n into, instead of this I am going to write n sigma squared divided by n, right? So now from this we can conclude that sigma squared is equal to sigma squared. Oh, okay, wait. So intuitively we have to understand that this expression is the sum of square treatment. So can you think how it can be possible, right? So here this is the standard deviation or the variance of yi dot. Okay, I is equal to 1 to a. Right? Okay, now this is the ith treatment variance, right? Ith treatment, the variance of ith treatment mean. If you, okay, so right, so okay, right, so now we know that this is the, this expression, let me use a different color. This expression is the standard deviation of ith group mean, right? So we can write yi dot bar is equal to summation I is equal to 1 to a yij minus yi yij divided by n, yij divided by n. Now summation yij is equal to n yi dot bar. This will not make any sense. Right. I will explain in a different way. Okay, now we know if you multiply something, an average by the sample size, it will give you the total, right? So now this is the one. Okay, now I have here you can see this is the standard deviation. I'm sorry, this is the variance of yi dot bar. Now if you multiply it by number of observation, it will literally give me the sum of square treatment, okay, sum of square treatment divided by a minus 1, that is the degrees of freedom. It will give me the ms treatment, right? So you have to remember that if you multiply the variance of yi dot bar by number of observation in that group, that is the treatment, that is the treatment, it will give you the sum of square treatment, and if you divide it by its degrees of freedom, it will give you the mean square treatment. Okay, right. Now, okay, so this is just a small proof. Now we will go for this intuitive approach. Thus these two estimates should be very similar. Well, hmm? ஓ போட்டாச்சு
உங்களுக்கு இந்த லாஸ்ட் பயன்பாடு எந்த அளவுக்கு இருக்கு கூடுதலா வருது அப்ப இந்த கருப்பு இது மாதிரி ஒன்று செஞ்சேன் அது எங்க கருப்பு மாதிரி பூச்சாடி மாதிரி சின்னதா ஒன்று செஞ்சேன் ஞாபகம் இருக்கா அது எங்க சரி இந்த ஹெட்செட் இப்போ தூக்கி தருவீங்க அப்புறம் தூக்கி எடுப்பீங்க அதுக்கு நீங்களே வச்சுக்கலாமே